Thank you to the organizers for inviting me to give lectures. I'm sorry I couldn't be there. I injured myself while training and have had pretty significant mobility issues. But I'm glad that I'm still able to give my talk through the magic of technology. And I'm glad you're here to listen to it. So let me tell you what we're going to do today. My talk is on my iPad so that I can annotate as we go. So I'll be looking down occasionally, but I'll also try to look at you as well. All right, we have many goals for the week, but today I want to introduce you to some of the key definitions. So it's a slightly heavy definition example day, but I've tried to break that up by giving you some exercises to do and some times where you can participate a little by shouting out. So today the goal is to survey many examples of lattice posets because I want to convince you that this is sort of a useful way to look at some of the combinatorial objects that the week is focusing on. We'll talk a lot about my favorite lattice poset, which is the Tamari lattice. Although today's talk will actually be centered a little bit more on permutations. Maybe some of this is familiar, but I hope some of it is new too. So we'll review some classic techniques for proving that if you have a poset, whether it is a lattice, which in general is a very tricky problem. And then we'll talk about a special property of some of the lattices we care about called semi-distributivity. And we'll see this as we'll be able to detect this through an edge labeling. All right. I also want to say that one of my goals for the week is to survey some of the people who work in this field as well, because I think one of my favorite talks that I ever attended as a postdoc was really about a mathematician. And I thought I would also include some people in these talks who work in this field. Okay, so these are our goals for today. We'll focus on many examples and the week order on permutations, and we'll hopefully end with an example with a connection between the week order on permutations and the Tamari lattice. So we'll be working a lot in the type A world. Okay, so some definitions that you're probably familiar with, but just to make sure we're on the same page for notation, we'll talk quite a bit about covering relations. So we say that X is covered by Y, and we write it as like a less than symbol with a dot. If X is less than Y in a poset, and there's sort of nothing between them. And then frequently we'll see that our posets have a biggest element, which I write with a 1 hat often, and a smallest element, which I write with a 0 hat. Okay, so far so good. So what is a lattice? We'll be using these words a lot today. So a lattice is a poset where for each pair of elements U and W, there's a smallest upper bound or join, which we write as like a big V, occasionally as like a small V between U and W. You can also think of this as the supremum, right? If that's something that's more familiar to you. And then dually, every pair of elements U and W has a greatest lower bound or a meet. Okay. So maybe those are familiar definitions, but maybe not. On the next couple of slides, we're just going to practice checking whether some small posets are actually lattice posets. So this is where I want you to shout out your thoughts, be totally shameless. I don't know, maybe you've had a coffee break. I think there's a coffee break actually after this, but just, yeah, I want to hear from you. Okay. Lattice or not a lattice?
Yes.
Yes. Okay, great, excellent. We're the most simple example, our classic example is subsets ordered by containment. The join operation is union, and the way to go down is intersection. Excellent. Okay. Couple of observations before we do another example. One is that when you take the join of a pair of comparable elements, sort of nothing interesting happens. you just get the bigger. If you take the meat of a pair of comparable elements, you get the smaller thing. And all of our posets will be finite. And so we can sort of recursively take joins of more and more things. And in this way, we could take the join of all of the elements of our lattice and, for example, the join. And so we must have something that is bigger than everybody, which is our biggest element. And then similarly, we can take the meat of everything, and we know there must be a smallest element. So all finite lattices have a biggest and smallest element. So all of my posets here should, otherwise it's not very interesting for you. All right, lattice or not a lattice?
Not lattice. Not.
I can't hear you. You have to be.
That's bow tie.
Yes, it is. No, it's not.
No.
No. Oh, great. Okay, excellent. Thank you. Right. So the pair of elements towards the bottom are atoms. There's two minimal common upper bounds, right? If we follow the edges up, they're both below 2, 3, 1, but they're also both below 3, 1, 2. And this is the strong Bruhat order on permutation, so not a lattice. I think this might be my last one. But I know we're having so much fun. What do you think? Take a minute. Yes, no. It's kind of non-planar, so it'd be kind of tricky.
Yes.
Yes. Yes.
Yes, excellent. That took some time though to check. Maybe some people were quietly saying yes, and then some braver souls decided to volunteer. So it sounds like consensus is yes. So this is actually the face poset of a small polytope. Maybe you can figure out what it is. But like the intersection of a pair of faces is still a face. So that might tell you, okay, at least there's going to be meets. And then we'll review in a minute that if you have one of those two operations, either the meet or the join, and you know you're kind of bounded, you have a biggest or smallest element, then that's actually enough to tell you you have a lattice. All right, so where we're going to go next is I'm going to show you several, I think, important examples of lattice posets having various properties. And maybe you've seen some of these in your own work. Partly I won't be focusing on all of these types of lattices, but I just want to give you a sense of how big the world is here and to help you recognize where these lattice posets show up elsewhere in the talks. So for example, a type of lattice, which I generally won't be focusing on today, is called a modular lattice. It satisfies a kind of associativity. You can see that I'm taking some joins and meets here in this equation. And there is an extra condition. I need A to be less than B. But the associativity is allowing me to move the parentheses from the X meet B over to the A join X. So this is a special property. And it appears kind of naturally in the mathematics world. The lattice of normal subgroups will always be this kind of modular lattice. And this has also appeared in recent work of Daisy Rock. So Daisy got her PhD relatively recently at Brandeis, works in kind of category theory and representation theory, where there's lots of exciting combinatorics happening. And with Eric Hansen has recently extended the notion of a composition series to modular lattices that are kind of arbitrarily large. So I really prefer to work in the very, very finite world, and Daisy's work is extremely not, because she's interested in representation theories that are continuous. So there's this sort of continuous cluster algebra thing that Daisy has been working on, so I think since her PhD. And so kind of being interested in composition series happening in a very infinite world was important. Okay, so that's a little brief digression. Let's see some other important lattice posets, some of which will come up for us. So the poset of order ideals, given a poset, I can look at all sets that are closed undergoing down. This is a lattice under containment, special type of lattice called a distributive lattice. We are also sometimes interested in intersections of hyperplanes. So geometric lattices are not modular, but they're semi-modular lattices with the property that every element is a join of atoms. And I know these have been important in the work of some of the people in this room. And it gives me an excuse also to show you a picture that I quite like. So I'm not sure if this is big enough. Maybe I can zoom in here. Yeah. All right. So now you can see a little better that I'm taking the intersection of hyperplanes, and those hyperplanes are indexed by all pairs of elements, all 2-element subsets of the numbers 1 through 4. So actually, this is a graphical arrangement, and this lattice poset is really just the partition lattice. It's a lattice. One way to see that at least you have joins. It's actually ordered by reverse containment. So going up, we can just take the intersection of any pair of elements, and we know we're still in this family of sets. And the hyperplanes that I'm taking here are the hyperplanes whose normal vectors all look like EI minus EJ. So sort of the type A roots. And I'm going to show you what these hyperplanes look like and what the intersections look like here. So here I have this beautiful picture of the graphical arrangement, or the type A Coxeter arrangement that I learned from Nathan Reading, who's also here. So what this picture is showing us is we take our hyperplanes, which are actually in R4, but they live in a subspace of R3. So we think of them as being 2-dimensional planes in a 3-dimensional vector space. And we intersect them with a sphere where they trace out great circles and then project those great circles onto the sheet of paper. And the intersections that we were seeing on the previous page appear as kind of these antipodal points that I'm not sure if you can see very well, so I'll highlight them in yellow as well. This would be an example of such an intersection. So if I have a collection of hyperplanes, like this collection here, and this collection happens to, all of these hyperplanes contain the origin. Another thing that I can do is look at the regions that they slice my space into. And that's another classic construction of a poset, which is sometimes a lattice. So this is called the poset of regions. And what I do is I choose a special base region, like this most central triangle here. So my hyperplanes in this example happen to cut space into sort of triangular simplices or simplicial cones. And the way that I order them is I take my base region and I orient all of the normal vectors of these hyperplanes that they point towards this base region. And so I can detect sort of where I am in this picture by taking the dot product or inner product of a vector in one of these regions with these normal vectors. And what I do is I collect up all of the normal vectors where my dot product is, say, negative. And now I've associated to each region here a set that I can order by containment. You'll notice that I also labeled the maximal cones here by permutations. And so this poset of regions also happens to be the weak order on Sn. And we'll kind of hint at how we can tell that this is a lattice. And there's actually a general theorem that if you have a poset of regions and that region you choose as the base region happens to be a simplicial cone, then the poset you get is a lattice. And then finally, my favorite lattice. This is the Tamari lattice, and we're the main character of our talks this week. We'll be building towards the connection to non-crossing partitions, which I guess is the title of this conference. So I should say non-crossing partitions at some point in my talk. Great, check that box. So this is a poset where I've ordered triangulations of a polygon based on the diagonals in the triangulation. So at the very bottom, I have this triangulation here where all of my slopes are negative, and I move up by removing one diagonal and exchanging it for the only other diagonal which does not cross anybody else, and which is less negative than I started with. Now I can also realize the Tamari lattice in multiple ways because the number of elements is Catalan many, and so you can sort of pick your favorite Catalan object and try to order it with the Tamari lattice. Another one that we'll be spending time with are certain pattern avoiding permutations. So these are 3-1-2 avoiding permutations, and we'll hopefully end the talk today by making a connection between the weak order and the permutations that we see here. Okay. So let's talk about some general techniques. If you're given a poset, how can you tell whether you have a lattice? I already hinted that if your poset is finite and has a largest element, all you have to do is check that meets exist. And there's a dual version of this in terms of joins. If your lattice is distributive, then you happen to always look like a poset of order ideals, that like one that we saw earlier. And this makes sense because then actually joins are just unions, meets are intersections, and we know those things distribute across each other. So we'll spend some more time talking about distributivity later in the talk. Another technique that is useful is thinking about your poset as a collection of subsets, which satisfy some kind of closure condition. And this is helpful because, as with the distributive lattices, which are just order ideals, when we take the intersection of closed sets, we're still closed. And so we kind of get our meet operation for free. And then one of my favorite techniques is called I guess I called this a theorem here. Sometimes this is also just a lemma. And it's that same condition that if meets exist and you have a top element, then you're a lattice, except boiled down to a kind of local check. So if you can check for every element Z covering X and Y, that the meet of X and Y exists, and you know you have a top element, then you're guaranteed to have a lattice. So I had originally actually planned to give you a short proof of this, which is inductive, but maybe I'll leave that as an exercise with another exercise for you. So I said we were going to spend some time talking about the weak order on the symmetric group. Let me remind you how this weak order works. So we'll write all of our permutations in one-line notation, and we move up by a cover relation in the weak order by looking for pairs of elements which are next to each other in position and in order in value. So for example, xi is less than the guy next to him, xi plus 1. So to move up, what we do is we just swap those two elements out of order. So there's a nice kind of local definition of what this weak order is. And then globally, we can also tell when a pair of permutations are ordered by checking containment of a certain set called the inversion set. And this is where we just look for all pairs of numbers, whether they're next to each other or not, which are out of order. So a pair of permutations x and z, x is less than z, as long as the inversion set of x is contained in the inversion set of z. Okay. So as a concrete example, if we look at our 2, 1, 3, we see that 1, 3 is in order. We can swap them out of order here to get 2, 3, 1. And my inversion set is just 1, 2 for this guy. For the top element, here my inversions are all pairs. So an exercise for you to try, since I'm giving like a lecture series, I feel like I need to give you some homework, is to prove, if you haven't done this before, that in general, the weak order on any SN is a lattice. So in this small hexagon, it's not so hard, right? Because most things are either comparable. If they're not comparable, it's very clear what the join and the meet are going to be. The join of on things which are not comparable is just the top element. So my hint to you is that it could be helpful to think about that kind of local condition about checking whether if I fix an element z and look at the things it covers, can I find the, say, the meat of those things? And I'll just give you a little hint about how this could work out, but you should go ahead and check it at home. You're going to sort of need to think about both the local definition of the weak order and the global definition at the same time. And maybe you have a different way of doing this too. Okay. So a little homework for you to try at home. In the last 20 minutes or so of the talk, I want to talk about semi-distributive lattices. So I mentioned distributive lattices, and those are probably familiar to you, but I put the definition here just so that we could stare at it. So a distributive lattice, in a distributive lattice, the join and the meet operations distribute across each other. And I also like to think of this as like, you can factor. In a distributive lattice, I see the x, a common x term, and I can factor it out. Okay. Let's see. This little Tamari lattice here, my favorite lattice, what do you think? Distributive or not distributive? Let's see if...
No.
I'm not sure. I think I maybe heard both answers there. So another exercise to check at home is that the person who yelled out, no, they were right. This is not distributive. And it's a minimal example of a non-distributive lattice. So any lattice poset that contains a pentagon, or even a pentagon as a sublattice, which means that these relations don't have to be cover relations, will never be distributive. Okay, but we're not talking about distributive lattices today. Actually, we'll talk more about them tomorrow. We're going to talk about semi-distributive lattices. So a semi-distributive lattice satisfies a weakening of that distributive law. So it says that sometimes you can factor, but the sometimes part is this if condition here. So I'm just going to focus on the join version of this join semi-distributive and leave it to you to know that, okay, I could swap these join and meet symbols and have a analogous definition, which is meet semi-distributive. Okay, so what is going on here? If in a special situation that x join y and x join z are equal, then you can factor. So what I mean is we could imagine distributing that x, and we would be looking at x join y, meet x join z. But now, if we look back at our if condition, those two things are equal. And when I take the meet of comparable elements, right, like nothing kind of happens, I just get the same thing I had before, I might as well just write it as x join y. And that's exactly what that semi-distributive law is saying. Right, so in the special case where I fix some x and I take the join with two other things and I just get the same thing back, I can factor. I can factor with the join and meet. So there's a meet version of this. And if your lattice happens to satisfy both this join version and the meet version, we just call it semi-distributive. Okay, so I don't know. I'm a very pictorial person, so I like to have examples and a picture of what these definitions mean. But just as a kind of a check that we're following along, what do you think? Does this lattice poset satisfy my join semi-distributive rule? Go ahead and shout it out.
Distributive, so.
Distributives.
Should be. I think I heard somebody say should be. It would be really kind of annoying to check this. Well, not very annoying for a computer, but you're right that it should be because it's distributive, right? Being distributive is stronger. This semi-distributive is a weakening of that, says you're satisfying this distributive law in a special case. So yes, you're right, it should be, and it is. Okay, this one's not so hard to check actually, like just looking at it because there's so much symmetry. So what do you think? Does this satisfy this join semi-distributive law? Yay or nay? Okay, but I want you to say it loudly and proudly.
Yes, yes.
Emily, people are saying things, but not loud enough for you to hear.
Oh, I really can't. So I was just gonna wait. What is the consensus? Can you like visually show me? Thumbs down, thumbs up?
Yes, yes.
Okay, Nathan is signaling, but obviously Nathan knows this. Others?
Okay, I'm going to say no.
You're gonna say no. Excellent. Thank you. Thank you.
Meet of two things and get zero, and then when you soup with something else, you don't go up anymore.
You're right. That's exactly right. Okay, so let's just write that down in case other people are staring at this. I'm never very quick when I'm listening to a talk, so I always appreciate it when somebody's takes some time with an example. So let's say that's my x, and we can call this y and z. It doesn't really matter because, right, there's so much symmetry here. And yeah, if I take x join y, that's the one that goes up, and there's only one way to go. There's the maximal element. And same with z. So x join y, x join z, we get the same thing. The if part is satisfied. But now, if I take the meet, that's the one that goes down. If I take the meet of y and z, there's only one place to go, and it's at the bottom. And now I'm taking, in this equation here, I'm taking x meet my bottom element. And remember, when you take the meet of comparable things, nothing interesting happens. You just take the smaller of the two.
You wanted X join the bottom element, right?
Oh, thank you. Yes. Okay, but I still take just the biggest thing of the two, which is x. And that is not the same as x join y, right? That was the top. Those guys are not equal. So this fails to be semi-distributive. This is also a non-crossing partition lattice. So again, we see our non-crossing partition lattice. Also a modular lattice that we saw earlier. Okay, but it's helpful to see this tiny example. Oh, I have one more. I forgot that I had this one. Now here, let's try to play a similar game. Let's say this guy's my X. And then Y, and now there's like kind of not a lot of things. If I want to satisfy the if part here, there's not a lot of choices that I have for the Z. So I'll just make this guy my Z. X join Y and X join Z both give me the top element. And if I take the meet of Y and Z, I just get the smaller of the two, which is Z. But again, that was the same as X join Y. So this maybe being a hexagon, maybe being such a small kind of polygon lattice seems a little silly, but this one also satisfies, this one does satisfy our joint semi-distributive rule, even though it is not distributive. Okay, so here's our visual intuition, which I think it's helpful if you think back to that modular lattice where we were failing the law. Right, so if we imagine that I have almost that modular lattice picture, the X, Y, and Z that we saw before, and they're all covered by some element A, right? X join Y, X join Z, they all land me at A. A is clearly the smallest common upper bound of these elements. Being semi-distributive means I should be able to take the meet of Y and Z and still kind of not end up below X. I still need to be able to take the join here with X and get back up to A. And so if we kind of continue this idea that if I have cover relations like this, I can keep going down, down, down. And since I'm finite, I know at some point that process has to end. There's always going to be some special element, which will be the smallest element, to join with that X and still land me up at A. And this special element happens to also be join irreducible. So let me remind you what a join irreducible element is in case this is not your area of study. So an element is join irreducible if whenever you try to write J as a join of some set A, actually that J had to be in there anyway. So it ends up being kind of one of these like silly joins. Equivalently, when you're a finite poset, which I always will be in these talks, J is join irreducible as long as it covers one element, which I like to write as J star. So if we think back to that visual intuition slide, whenever I have a cover relation A down to some element X, I should be able to take meets of the other covers and sort of keep going down, always joining with X back up to A until that process must terminate. It has to because I'm finite. And it will terminate at a joint irreducible element J, which satisfies if you go down just one more step, now you are below X. So this is a criterion to check whether your lattice is join semi-distributive. And I like to encode it as a labeling of our cover relations. So now this cover relation between A and X, I can label with my join irreducible element J. You might wonder, like, well, what happens when A is just join irreducible? Then the label is just A itself. Okay, so we can apply this idea to our small weak order example. I have 4 join irreducible elements, which I will highlight. You can find them because there's only one way to go down. I know that the way I'm supposed to label joint irreducible elements is just by that joint irreducible itself. So I'll go ahead and do that. And that leaves only 2 labels left. Okay, so we'll have to think a little bit about what that labeling, how is it supposed to work? So what you do is you fix your A, you go down to your X, and you look for the smallest element such that X join that smallest element is still getting you up to the top. Okay. So turn to your neighbor. What would be the smallest element for this X, 2, 3, 1? What would the label be?
1, 3, 2.
Very good. Excellent. And then by symmetry, the other side is going to be labeled. Let me keep my red labeling. 2, 1, 3. Very nice. Okay, so that was a nice small example where you could do everything explicitly. I want to give you the tools to be able to do this in general, because you have some homework already to do for the week order. I might as well really understand what this lattice poset is like. So remember, we write our permutations in one-line notation. Inversions are pairs of numbers that are out of order, but some of those inversions are special, and they're called descents. So a descent is a pair that's out of order, but they're also right next to each other. So they came from a cover relation. Remember, a joint irreducible element has only one lower cover, only one way to go down. And so every joint irreducible permutation has exactly one descent. And so those descents kind of tell us everything about our joint irreducible elements. And I will demonstrate this with a small example. So here I have a permutation in S7. I think it's a permutation 1, 2, 3, 4, 5, 6, 7. Good. And I've highlighted the 3 descents, which are going to correspond to 3 cover relations. And for each descent, I can write down a corresponding joint irreducible permutation. The yellow will be the joint irreducible permutation with a 3-1 descent. And the other information that I need is I look at the numbers between 1 and 3 in this example. There's only one number between 1 and 3, it's 2. And I check to see where is the 2 relative to that descent in this permutation. It's over here. It's to the right. So I'm going to put the 2 on the right side of this descent. And then I'm going to write all of the other numbers in order because I don't want any other descents in my permutation. Okay, let's go ahead and do the 5, 7. So 5, 7, I've got that 5, 7 descent, which I guess I'll write as 7, 5. I look for the numbers between 5 and 7. There's only 6. And I check what side of that 5, 7 descent is the 6. It's on the left side. And now I need to write all of the other numbers in increasing order so that I don't make any new descents. They're all smaller than 6, 7, 5. So I'm going to put them all to the right, or sorry, to the left. And now 2 and 6, there's many numbers that are between 2 and 6. Some of them are to the left and some of them are to the right. So 5 is to the right. 1 and 3 are to the left. I'm not writing them, so I'm writing all of these numbers in order because I don't want to introduce any extra.
3 and 4.
Oh, good, thank you. Now I think I'm just missing one number to make it a permutation in S7, and I'm going to stick that at the end again so I don't make extra descents. So I've given you a kind of recipe now to label every cover relation by a joint irreducible element. And I think you also, based on the slides, what we know about the weak order can check that if I take the join of, say, this guy and this join irreducible, I will go to this element here we can call A. And the reason why is because kind of the only inversion we're missing from this 1, 3, 4, 6, 2, 7, 5 guy is the 3, 1 that is in our join irreducible. And that's true for the other cover relations as well. So this is a little bit of a sketch, but I wrote down the whole labeling for S4. So if you want to do this at home and then check your work with my slides, you can. I want to say that this gives us a proof that the weak order is semi-distributive. My labeling shows you that it is join semi-distributive. This poset happens to be self-dual, meaning that if I pick it up and flip it over, I get an isomorphic poset. So I get the meet version of this as well. Being both join semi-distributive and meet semi-distributive tells me I am semi-distributive. Okay, I am almost out of time, so I'm going to give you some more things to play with and end with a quick connection between the Tamari lattice, which I hope to really focus on in these talks, and the weak order. So let me remind you, the Tamari lattice, we realize, I'm going to be realizing as a poset of triangulations where you order the diagonals based on their slope, or as a collection of pattern avoiding permutations where we're avoiding the 3, 1, 2 pattern. So you could play around with this. I'm curious. We already know that this is not distributive, but can you see that this is a lattice in general? If you draw out the next higher dimension version of this, it's really not quite so clear. Okay, so here's my connection to the weak order. I'm going to zoom past this slide. I'm going to describe a map that I learned from Nathan Reading from permutations to triangulation. So here's the recipe. You give me any permutation of the numbers 1 through n, let's say, and then I'm going to draw a polygon where I have a long edge labeled 0 to n plus 1. So one bigger than the permutation you gave me. And then below this, I'm going to put the numbers 1, 2, 3 in order up to n. And now you hand me a permutation, and I start out by just tracing out the path under my 0 to n plus 1. And then I look at my permutation and I look for the first number I see. And I trace out the same path before, except that I'm going to skip that first number in my path. So in this small example, I traced out a path from 0 to 4 along the bottom. And then I'm going to redo it, except when I get to 2, I'll skip. Go straight to 3, and then 4. Just like here. And I repeat that process one number at a time. So now I've got a path from 0 to 4. It skips 2. And the next number I see, I will skip. So the next number I see is a 1. I start at 0. I would usually go through the 1, but I'm going to skip it, go straight to 3, and then 4. And then finally, I have a path from 0 to 4. It goes through 3. That's the last number in my permutation I see. I skip it. And this traces out a triangulation. It turns out this process will give me every possible triangulation. There are more permutations than there are triangulations. And so some permutations give me the same triangulation. I encourage you to play with this at home and see which permutations do give you really the same triangulation. I gave this problem to an undergraduate recently, and they kind of made the key observations. We'll spend some time talking about this map tomorrow and a little bit more about the Tamari lattice. But I think I will go ahead and end here. Thank you all for participating. And I look forward to the week of this conference.